Welcome back, Virtual Earth Space Science. So we've been talking a lot about the theory behind how stars remain stable and how they evolve throughout their lifetimes. But in science, it's very important that any theory be tested through experiment or observation. This is actually one of the most important things about science. Theory makes predictions and pushes the frontier of our knowledge, but experiment is necessary to test and ground that theory to make sure that it's true and reasonable. This is the essence of science. Well, astronomy is a special kind of science because it's very difficult to arrange an experiment the way you would like it to be in astronomy. You can't move the stars to where you would like them to be. You can't change them directly, so you just have to make do with what you can observe and observe in a clever way. You really don't have control over what's going on up there, except you can choose what you want to observe. It turns out that observing a cluster of stars is a really good idea, and that cluster is a perfect laboratory to use as a test of stellar evolution theories. There are lots of reasons for this. First of all, there are many stars in a cluster, and so you can observe many of them all at once, which is convenient. But also, these stars are at roughly the same average distance from us. Although some of them are slightly closer and some of them are slightly further away, they are all together probably much further away than those differences, and so their distance from us is more or less the same. Also, they come from the same cloud of gas and dust, and so any peculiarities in their composition are probably shared among all the stars. And finally, they were all formed at roughly the same time, and so that is another variable that is taken out of consideration. They should all be roughly the same age. So I think it's time to take a look at some of these clusters of stars to get an idea of what I'm talking about. This is the Pleiades, one of the nearest open star clusters to us. It's about 450 light years away, and it's only about 45 light years in size. We can actually see this pretty easily in the night sky if it's the right time of year, and if I ever get back to Tana, I'll show you guys. It's really beautiful through a small telescope. Anyway, it's got a few hundred stars in it. The fact that some of these stars are very blue and big stars means that it must be very young, because such stars don't live very long. It's thought that our Sun probably formed in a cluster very similar to this one, some 4 billion years ago. Most stars, it seems, as far as we can tell, do form inside clusters of stars. So stars form in groups, and it's thought that our Sun also formed in a group. Even though the O stars are the brightest ones and the easiest to see, if we look carefully we find that there are actually very few O stars and many, many, many more smaller M stars. This is a totally different kind of cluster. It's called a globular cluster, and it's thought that these things could be older than our entire galaxy. They can contain millions of stars and are virtual small galaxies of their own. There are lots of these things floating around the outskirts of our galaxy. We don't think our Sun formed in one of these. These clusters of stars may be some of the oldest objects in the known universe. This is another open cluster, like the Pleiades. Not nearly as many, maybe tens to hundreds of stars. The fact that these clusters are all about the same distance from us means that when we measure their apparent magnitudes, we can use those to compare the luminosities, the intrinsic or real absolute luminosities of these things. Here's another beautiful cluster called the double cluster, two open clusters near each other from our line of sight. And so let's find out how studying the luminosities and colors of these stars can help us learn something about the age and distance of these clusters and what's going on in terms of evolution of these stars. Well, one important thing to bring up is that observations of clusters very definitively confirm the theory that we've talked about. So the stellar theory agrees with observations very well. And the observations that astronomers take of these stars clusters are of two types. First, they measure the apparent magnitude, which tells us, like I said, because the stars are all at the same distance, that tells us their relative luminosities. And then they measure the colors of the stars, which, as you know, corresponds to the temperature. So these two guys, Mr. Hertzsprung and Mr. Russell, right around the same time, figured out the same sort of graph. And so the graph is named after both of them. It's called the Hertzsprung-Russell diagram, but that's a lot to say, and so it's often abbreviated an HR diagram for the first letter of each of their names. And it's also sometimes called a color magnitude diagram, since that's the measurements from which it originally comes. And so what happens is a particular star on this diagram will, throughout its lifetime, move around. As an example, well, first I need to talk about the axes. The vertical axis is luminosity, with the brightest stars being on top and the dimmest stars on the bottom. And temperature is on the other axis, the horizontal axis, with the hottest stars on the left, which is a bit weird. Blue hot stars on the left and cooler stars on the right. Anyway, protostars, young stars that aren't yet quite stars, that are still in the process of being born, are usually kind of high in this diagram, and as they stabilize and turn into main sequence stars, they move downward. And that's what I'm trying to indicate here. This dashed line here represents the main sequence along which most stars will eventually spend most of their lives. I've tried to indicate by the length of the arrows that the O stars evolve much faster and the M stars much slower. In fact, O stars, as we know, are big, and so they burn, really live fast and die young. They're born, live, and die before M stars are even really on the main sequence. In this diagram, I've tried to illustrate the typical path that a star will follow in a color magnitude or HR diagram. Starting above the line where you see the number 1 is the protostar phase of life. As the star turns into a main sequence fusion star, it drops down onto the main sequence where you see a 2, and it spends most of its life there. When it begins to die, it generally moves up and to the right into some sort of red giant phase where you see the number 3, and then very rapidly jumps down below the main sequence to the number 4, where it becomes some sort of stellar remnant. For a star like our Sun, that would be a white dwarf. And as time passes, it cools and dims and slowly moves down and to the right. You're going to get a chance to see some better simulations of this in the simulations that I'm pointing you to in the PDF file. Now, if we look at a whole cluster of stars, there's going to be a lot of stuff going on at once. But the thing that I want you to notice is that the high mass stars, which would be at the top left of this diagram with high luminosity and hot temperatures, the O stars, they're going to evolve very quickly. They're going to blow up and turn into remnants on the bottom left corner of the diagram very quickly. And as time passes, the main sequence of stars is going to sort of peel off away from the main sequence. And you're going to see that in those simulations. And the stars on the bottom right of this diagram, the M stars, are going to evolve very slowly. You're not really going to see any change at all. But there'll be a steady peeling off of this main sequence from left to right as the stars move up and become red giants and then either experience a supernova or planetary nebula phase and turn into stellar remnants. Now we're going to talk more about stellar remnants in the next lesson, but some more interesting things about studying clusters is because these diagrams follow a very predictable and repeatable pattern, we can study these kind of diagrams to figure out the age of a cluster. How far down has the main sequence peeled? That actually turns out to be a very good way to determine how old the cluster is. And also the distance. We can compare the HR diagram of a cluster with a known distance to one with an unknown distance and sort of shift them around to figure out how far away the unknown one is. I've actually done this when I was in graduate school. It's not too bad and it's kind of fun. Alright, so from here I'd like you to download that PDF file and explore those HR diagram simulations, and then go to the other website and read through and answer the questions. Just please follow the directions in the Blackboard assignment listing for this week. Have a great week, guys. Talk to you next time.